Major support for Stormwatch was provided by the Meadows Foundation and was produced as a joint venture between the National Weather Service and the Texas Severe Storms Association.
The following is the North Texas Severe Weather Outlook issued by the National Weather Service Forecast Office in Fort Worth at 6:25 a.m. There is a high risk of severe thunderstorms this afternoon and tonight for the extreme northern part of North Texas, generally north of a line from Texarkana to Denton to Haskell. There is a slight risk of severe thunderstorms for the remainder of North Texas, including all locations north of a Brady, Belton, Hempel line. An intensely strong upper-level disturbance will move across North Texas today, and as it does, strong to severe thunderstorms will develop in the unstable air mass, which is already in place. Due to the pronounced turning of winds with height, especially over the high-risk area, and a significant dry air intrusion, supercell thunderstorms are likely to form. Some of these could produce strong tornadoes. Emergency management officials and storm spotters across the western and central parts of North Texas should be ready for possible activation this afternoon. Stay tuned to NOAA Weather Radio for additional information concerning this potentially dangerous weather situation.
Hello, this is Sam.
Sam, it looks like it may be a rough one today.
Yeah, I know. I heard the early morning outlook. I think I'll wait till the watch is issued and take off then.
Good. We may need everyone on this one. I'll be in the Emergency Operations Center all day if you need me. Okay, fine.
In these areas. Remember, a tornado watch means conditions are favorable for tornadoes and severe thunderstorms in and near the watch area. Stay tuned to NOAA Weather Radio for later statements and possible warnings.
This is K5KJ. Go ahead, Weather Service.
Sam, things are heating up here. The radar indicates circulation over Benbrook.
The Weather Service is issuing a tornado warning for Tarrant County.
Okay, I'm heading that way. This is K5KJ.
Roger, K5KJ. Dallas EOC, do you copy?
Dallas COC copies.
There's definitely strong rotation in that storm, but it's difficult to interpret the data because it's so close to the radar site.
Weather Service, this is K5KJ. I'm in the Edgecliff area and can see the storm clearly. There's a definite wall cloud and rotating debris underneath.
This is a severe weather statement. At 9:02 p.m., a tornado was reported on the ground near Cedar Hill. This was verified by amateur radio spotters.
The storm's just west of Lancaster, moving east at 30.
Weather Service, this is K5KJ.
This is WB5FLQ National Weather Service. Go ahead, K5KJ.
I'm near Lancaster and I can see transformers exploding in this area.
Roger, K5KJ. Dallas EOC, do you copy?
EOC copies. Net, be advised, Lancaster EOC has activated their sirens.
Mom, there's something out there. Josh, get away from that door. Weather radio says there's a tornado coming. Now get in the hot closet. But Mom, hurry.
This is K5KJ. Paratornado is moving into Lancaster.
Roger, K5KJ.
All stations stand by. Station break, identify, and go ahead.
65, Young Bravo Charlie, I'm at 35 Belmont. I'm
If no basement is available, seek shelter in an interior room, such as a closet on the lowest floor.
A complex and delicate balance of atmospheric ingredients is required for the production of nature's most violent thunderstorms. National Weather Service forecasters have acquired the tools of late 20th century technology to aid them in predicting and tracking dangerous storms. Highly refined computer models help to forecast severe weather events several hours and even days in advance. The high-tech WSR-88D Doppler radar assists Weather Service personnel in the short-term prediction of storm movement and evolution. Despite these assets, the National Weather Service still depends heavily on one of its oldest allies when severe weather threatens. Storm spotters act as the eyes of the Weather Service when dangerous storms are imminent in a local area. The spotter relays eyewitness accounts of severe weather activity in real time to the National Weather Service and to local emergency management agencies. Their information is essential to the success of a local weather warning system. They must be thoroughly knowledgeable of severe weather phenomena. The environment in which thunderstorms develop is critical in determining storm structure, lifespan, and intensity. 3 atmospheric conditions are necessary for thunderstorm formation. First, moisture must be present, usually in the lower 10,000 feet of the atmosphere. Second, the atmosphere must be unstable. By definition, unstable air accelerates up or down after it's given an initial push in either direction. On a typical severe weather day, the unstable atmosphere has a layer of warm, muggy air close to the ground, with relatively cold air above. Third, a source of lift must be present to initiate thunderstorms. The lift source is usually a front, a dry line, an outflow boundary from previous thunderstorms, a sea breeze, or even mountains. Generally, as instability increases, the strength of a storm's updraft and downdraft increases, and the storm is more capable of producing severe weather. Storms which develop in very moist environments often produce copious rainfall. Those which form in relatively dry atmospheres, more typical of the western United States, often produce little rainfall, but rather gusty winds and fire-starting lightning. However, under certain conditions, western areas may experience very wet atmospheres and flash flooding, whereas eastern states occasionally may receive high wind gusts from so-called dry thunderstorms. The amount of vertical wind shear, or change of wind direction and/or speed with height, is crucial in determining a storm's structure and lifespan. When the vertical wind shear is small, storms with short-lived updrafts occur. Inflow into the storm is weak, and precipitation falls through the storm's vertically erect updraft. This storm resembles the single-cell storm, depicted in the thunderstorm spectrum. In reality, the single-cell storm is better described as an unorganized multi-cell storm with cool outflow lifting new updrafts in seemingly random fashion around the initial storm cell.
Increasing values of vertical wind shear have adverse effects on clouds and storms with weak updrafts, literally shearing the towers from their cloud bases. Storms with strong updrafts more easily withstand the destructive forces of vertical wind shear. The strength of the updraft and winds aloft allows precipitation to fall downstream rather than directly through the updraft, enabling the storm to become relatively long-lived. This animation simulates airflow as it typically exists in a sustained thunderstorm. The red particles represent rising air. The blue particles denote falling air. These storms may become organized multicell or even supercell storms.
Organized multi-cell storms may occur as isolated clusters of updrafts and downdrafts, with an organized lifting zone of new updrafts generally on the right flank, as seen moving with the storm. New updraft formation in the lifting zone causes this storm to approach the camera, even though winds aloft clearly move cloud elements from left to right. Resulting deviations in storm movement can occur either to the right or to the left of the original storm motion. Organized storms also occur in squall lines, with the organized lifting zone on the front flank, generally above the shelf or roll cloud formation. Both types of organized multicell storms may last for hours because of updraft regeneration, producing hail to golf ball size, damaging winds, flash floods, and weak tornadoes. Severe weather typically occurs near the updraft-downdraft interface. Storms with strongly rotating updrafts, also known as supercells, develop when the wind veers or turns in a clockwise direction through the lowest mile of the atmosphere. When the wind speed is sufficiently strong and veering with height is present, horizontally oriented rolls develop in the lower levels of the atmosphere. When these rolls are tilted by a thunderstorm updraft into rotation about a vertical axis, a mesocyclone may develop. A mesocyclone is defined as an area of deep storm scale rotation, usually associated with a strong updraft. The area near a mesocyclone is the preferred region for severe weather. Rotation can increase updraft and downdraft velocities significantly, leading to violent weather such as tornadoes, giant hail, intense downbursts, and torrential rainfall. Over 90% of mesocyclones produce severe weather, and about 50% produce tornadoes.
Non-tornadic events, such as flash floods, large hail, and downbursts, are much more common than tornadoes and represent a significant threat to life and property in their own right. A flash flood is a rapid rise of water, usually caused from excessive thunderstorm rainfall. Flash flooding is produced by large, slow-moving storms or by train effect storms. Organized multicell storm updrafts can produce a train effect by reaching maturity as they sequentially move across the same area. Remember that flash flooding is most dangerous at night, when the effects of flooding are very difficult to see. When spotting, avoid low water crossings and don't drive into water-covered areas.
A downburst is another non-tornadic event that often occurs in severe thunderstorms. It is a strong downdraft with an outrush of damaging winds on or near the ground. Large downbursts more than 2.5 miles across are called macrobursts. Intense, long-lived macrobursts are known as derechos and may produce winds exceeding 100 miles per hour. This is a computer simulation of a microburst, a downburst less than 2.5 miles across. Microbursts are dangerous to aviation and lightweight structures. The horizontal roll vortex, or curl, which marks a microburst's most dangerous stage, is evident in both the simulation and this time-lapse photography of a microburst. A rainfoot, or outward distortion of the edge of a precipitation shaft where it strikes the ground, is a visual clue of a possible microburst. A plume of dust raised from the ground, known as a dust foot, may also mark the presence of a microburst. Virga, precipitation that evaporates before reaching the ground, and small, intense rain shafts also hint at potential areas of downburst formation. This is a downburst as depicted by the WSR-88D, the National Weather Service Doppler weather radar. The reflectivity, or precipitation display, shows a bow-shaped echo caused by the downburst winds. The bright green areas on the velocity display indicate strong winds blowing inbound or toward the radar. In this case, storm spotters observing an event like this would see a well-developed shelf cloud marking the gust front and strong winds as it passed overhead. Hailstones form in thunderstorms with strong, persistent updrafts. Hail larger than 1 inch in diameter may damage windshields, so avoid hail when spotting. Giant hail larger than 2 inches in diameter can cause enormous damage. Such hail almost always is associated with a mesocyclone, inferring the potential of tornadoes and strong downbursts. When giant hail is observed in your area, look for signs of storm-scale rotation and possibly even a tornado. A fundamental challenge when spotting thunderstorms is to assess visually a storm's potential for producing severe weather. As discussed earlier, a strong updraft and storm-scale rotation are two primary factors which enable a storm to become extremely severe. There are visual clues to help in your assessment of a storm's updraft and its potential for rotation. An important feature to identify is the rain-free base, an area of relatively smooth, flat cloud base from which little or no visible precipitation is falling. The rain-free base marks the area of inflow, where warm and moist air enters the storm. From a distance, vertical cloud towers may be seen rising above the rain-free base. As the storm intensifies, the updraft draws in warm air and some rain-cooled air. The water vapor of the rain-cooled air condenses more quickly than the warm air, forming the lowering of the rain-free base called the wall cloud. Updraft ingestion of rain-cooled air into the wall cloud is often visible as a tail cloud. Mid-level cloud features which suggest a strong updraft include a hard, solid appearance and a nearly vertical orientation of the main storm tower. A flanking line of smaller cloud towers may extend south or southwest of the main storm tower. The flanking line suggests that persistent lifting is occurring on one flank of the storm and important storm scale organization is present. If the upper portions of the storm are visible, look for a thick, smooth-edged cumuliform anvil and a large overshooting top, which persists for more than a few minutes. These clues suggest a strong updraft. When the anvil streams away from the storm in one particular direction, upper-level winds are probably strong, and the storm updraft is well ventilated, traits of a long-lived storm complex. In spite of strong winds aloft, these intense updrafts often produce back-sheared anvils above the storm's rear flank. With the most vigorous updrafts, thick knuckle-like protuberances are often seen on the underside of the anvil. These upper-level features are difficult to see when haze and low clouds obscure the spotter's view. Visual clues which suggest storm scale rotation are in the storm's lower and mid levels. The most important of these clues is the presence of a rotating wall cloud. The area near a rotating wall cloud should be watched closely for giant hail, extreme downbursts, and possibly tornadoes. Another significant cloud, the so-called beaver's tail, is a smooth, flat cloud band which often extends from the eastern edge of the rain-free base to the northeast or east, adjacent to the precipitation area. While not always present, the beaver's tail is suggestive of strong inflow into a rotating storm. Striations on the cloud base and/or main storm tower may give the entire storm a corkscrew or barber pole appearance. Mid-level cloud bands may also be present, encircling the updraft tower like rings around a planet. These visual clues strongly suggest the presence of a mesocyclone or supercell storm. This is a supercell thunderstorm depicted at 4 different heights on the WSR 88D. The lower-level reflectivity displays in the upper panels show the classic hook associated with supercell storms. The mid-level reflectivity display in the lower left panel indicates a bounded weak echo region, or BWIR. The BWIR is a radar signature of an intense updraft, probably one associated with a supercell storm. The low-level velocity display shows strong inbound winds next to the strong outbound flow. This inbound-outbound couplet is an indication of the mesocyclone's rotation. At this time, the storm gave ample visual evidence of rotation, including a large, violent tornado in Noble County, Oklahoma. 3 years later, another storm exhibited similar WSR 88D characteristics. The resulting violent tornado took 20 lives in northern Alabama. These Doppler radar signatures allow the Weather Service to issue tornado warnings before each of these tornadoes. Storm spotters then provided critical reports of tornado touchdowns.
Most strong and violent tornadoes are spawned by mesocyclones. Prior to tornado formation, a wall cloud usually forms, displaying several characteristics: persistence, sustained rotation for 10 to 20 minutes or so, surface inflow of 25 to 35 miles per hour or stronger, and rapid vertical motions. Many tornadic wall clouds are visually well developed and blocky in appearance, but they can be quite shallow at times and hard to distinguish from a distance. Many tornadic circulations form at mid-levels and gradually build up and down with time. However, others apparently form in the mesocyclone's low levels. Whichever formative route is taken, a downdraft develops in the mid-levels at the rear of the mesocyclone. Many times, a rear flank downdraft, or RFD, will descend as a low-level tornado circulation spins up. The RFD may reveal itself as a clear slot or a bright slot to the immediate right rear of the wall cloud.
When the tornadic circulation reaches ground, an ample supply of warm, moist air flows into the tornado. After impacting the surface, the RFD wraps around the tornado, gradually cutting off the inflow. Intense downbursts often result from the RFD's gust front as it progresses around the right flank of the tornado. Because its inflow is disrupted, the tornado begins to decay. The condensation funnel decreases in size, tilts with height, and takes on a rope-like appearance before dissipating. After this so-called occlusion of the mesocyclone, subsequent mesocyclones and tornadoes may form further east, resulting in a cyclic supercell. Subsequent tornadoes usually form within minutes after the previous tornado has lifted. Shortly after this violent tornado in southeast Illinois dissipated, the parent supercell produced a smaller tornado in southern Indiana. The rope-like tornado weakened quickly as a new wall cloud formed on the gust front to the east-northeast. Within minutes, the wall cloud spawned a new tornado as the cyclic process continued. The supercell discussed earlier can be termed a classic supercell and serves as a baseline when discussing supercell variations. Much has been made recently of low precipitation and high precipitation supercells, which might suggest that those are truly different kinds of supercells. Actually, the most important consideration is that all of these variations are supercells and possess mesocyclones capable of producing extremely dangerous weather. Storm spotters and meteorologists who understand supercell variations have the best chance of identifying a supercell. High precipitation supercells have more precipitation falling through and near the mesocyclone than do classic supercells. The abundance of precipitation in the mesocyclone often makes spotting difficult. From 8 miles, we're looking west at a large HP supercell. The mesocyclone is on the east side of the storm, with heavy precipitation to the west, behind the mesocyclone in this view. Note the rotating mid-level cloud bands and striations. Strong easterly inflow was ripping across the fields into the storm. The mesocyclone and a tornado occurred in this part of the storm to the immediate left of the Beaver's Tail. Lack of backlighting, in addition to wrapping rain curtains, made the large tornado difficult to see. Another HP supercell near Amarillo produced wrapping rain curtains to the immediate south of an area of converging inflow and strong rotation. Within 15 minutes, a wall cloud and then a tornado formed, partially obscured by low cloud bases and swirling mesocyclone rain shafts.
Many times, the only view that a storm spotter will have of a tornado with an HP supercell is looking west or southwest into the notch. Okay, the notch is that portion of the updraft where the tornado is not completely rain-wrapped. Viewing the updraft at right angles to its forward motion usually results in total obscuring of the updraft's wall clouds and tornadoes by wrapping precipitation curtains.
Spotters are strongly advised not to drive into a rain-filled HP updraft looking for a tornado. HP supercells frequently have striations around the main storm tower, mid-level rotating cloud bands, and a Beaver's Tail. Thus, although events under the cloud base are difficult to discern, ample evidence often exists to confirm that the storm is a supercell. It was once thought that HP supercells occurred mainly in the southeast U.S., such as the one that produced this rain-wrapped tornado in Tampa, Florida. But they've been documented in all parts of the country. In fact, there is evidence that HP supercells may be the most common form of supercell nationwide. Unlike HP storms, low precipitation supercells produce relatively little liquid precipitation. However, they often produce large hail. They're most commonly seen on the high plains near a dry line, but they've been documented in other areas as well. LP supercells can be difficult to detect on radar, but they're fairly easy to identify visually. The main storm tower is usually thin, bell-shaped, or flared out close to the cloud base. with striations on the main storm tower. LP supercells often produce wall clouds and occasionally spawn tornadoes. The typical low precipitation supercell has a translucent main precipitation area. Spotters should be wary of the benign appearance of the precipitation. Giant hail may be falling to the immediate northeast of the storm tower in an area that appears to be rain-free. LP supercell downdrafts usually are weak, thus downbursts are rare. Non-supercell thunderstorms are capable of producing weak tornadoes and other tornado-like vortices which can be quite dangerous. In warm coastal areas, the most common of these vortices is the waterspout. A waterspout is a small, intense vortex over water. Waterspouts form as cumulus clouds develop rapidly over areas of convergence and horizontal wind shear. Waterspouts are generally weaker than tornadoes, although they can have winds up to 140 miles an hour. Land spouts develop in a manner similar to waterspouts under developing cumulus clouds that grow over areas of convergence and horizontal wind shear. It's believed that many of the weak non-supercell tornadoes are actually land spouts. Nevertheless, they can be life-threatening and should be reported. Although mesocyclones are not required for the development of land spouts, land spout-type tornadoes can occur within a few miles of mesocyclones. These poorly understood events can cause coordination problems between spotters and radar operators. Gustnadoes are small vortices that sometimes form along gust fronts. They do not extend to the cloud base and are small and usually quite brief. They can cause damage to lightweight structures, so they may pose a threat to people in their path. The storm spotter plays a crucial role in the early detection of dangerous storms. Their knowledge of severe weather phenomena makes them a valuable asset to the National Weather Service and local emergency management agencies. And a guardian of what really makes their job so important. To obtain a copy of Stormwatch, contact the Texas Severe Storms Association, or TESSA, at Post Office Box 122222, Arlington, Texas 76012. To learn more about severe weather, contact your local National Weather Service office or one of these educational sources.